Okay, moving on. On page 42, they talk about the closest pair. So I'm going to show, here's a good example. Here's a whole bunch of dots, and I want to know which one of those dots is the closest together, the closest pair. Well, if you just kind of look at this, you go, ah, man, there's 12 dots there. I don't even know where to begin. I guess the brute force approach would be just go in there and look at the x and y coordinates, and figure out the distance, and then do like smaller. So this one plus that, this one and that one, no, this one and this one, this one and this one, this one and this one, then move on to that one. This one and this one, this one and this one, this one, then move on to this one. So here's the brute force, whatever hunting for the smallest distance. And so for I to N, and then do it again and get the square root of the squares. Remember the distances, the square root of the sum of the squares. And then if it's smaller, then go through your business. Now, the problem with this is, if you kind of look at this, you can probably tell that is not very efficient. And in fact, if you were to look at the big O notation, this would be one of those big O notations where it would be big O sub n factorial. In other words, adding one more dot is going to make this thing a heck of a lot more inefficient. Okay? So just kind of eyeballing the problem, brute force is, absolutely horrible for performance. But let's talk about divide and conquer. Okay? Let's say I broke it up into, if I gave you just these three dots and said, which one of these is the closest? That'd be a really trivial problem, wouldn't it? Which one of these is the closest? That'd be kind of trivial. Which one of these is the closest? That would be trivial. So see what we're doing? We're just like the tournament method. We're taking two teams, except this case it's three dots. Which one of those three dots? And then we move over. Which one of these three dots? Which one of these three dots? We made the problem trivial by dividing it up. Instead of looking at the whole thing going, I don't even know where to start, I just say, pick three dots, check them out. Pick three dots, check them out. Pick three dots. So this one's going to have one of those scenarios where I divide the problem, and then I do the work, and then I combine the answers together, because there's only going to be one answer, right? Okay, good. So the technique would be create two lists if you wanted to do this. Sorted by X and others sorted by Y. And then the best case scenario is to have only three dots in your thing, because that makes it trivial. If I can make a complex problem trivial by using divide and conquer, this is going to work really nicely. And it's going to be a heck of a lot more efficient than a big O of n factorial. Okay, so I'm going to look at this next guy. Whoop, no, don't. So, you see what we're doing? We're breaking this thing up into small chunks so that it's easy. This technique is the brute force technique, and that's just not going to work. Now, I'm not actually going to show you the technique for actually doing the breaking up, but you can kind of sort of figure it out. Just pick three of them, and then pick three, and pick three, and pick three. You could do it by any technique you wanted. Okay. So, this is a good example of the divide and conquer. Okay. Now, moving on. Page 47, they talk about something called a convex hull. These are good mathematics terms, okay? If you're not a mathematician, you're going to be going, what are all these weird words? Well, okay. A convex hull. So a convex hull is, I've got a bunch of dots, okay? And I want to know the circumference of the dots. Now, look at it this way. Let's say you had a board that had a bunch of nails stuck in it, okay, randomly. And you had a rubber band, and you want to put a rubber band around all the nails. Okay? So you stretch the rubber band around all of the nails. So make sure there's no nail that's not being, held in by the rubber band. That is what's called a convex hull. It's the perimeter, outside perimeter of a bunch of dots. Okay? A concave hull is where, I could take the rubber band and kind of go pick up this guy over here and pick up this guy over here. So one of the techniques, there's only one. Can you kind of see if you had nails in a board and I told you I want to put a rubber band around all the nails. Isn't it fairly obvious there's only one answer? There's only one correct answer. So there's only one convex hull. But then I said, oh, but it's perfectly okay for you to, reach into the thing and wrap a rubber band around something else. Now, there could be lots of convex hulls. Okay, one more time. There can only be one Oh, did I say that wrong? There can only be one convex hull, but you can have lots of concave hulls. Okay, got it? Good. Okay, so how would you do that? I mean, mathematically, how would you go in there and do this? So I have 19 points. And so the technique they talk about is the brute force approach. And the brute force approach is not quite as bad as the other, but it's going to be a big O of n squared. Okay, that's a lot. And so, again, it would be like, well, is that going to work? No. Is that going to work? No. Is that going to work? No. You just kind of go through it and check every single one of them to see which one makes the outside perimeter. But the divide and conquer one, I'm not going to go through all the details because it's kind of boring. But in the book, they talk about how you pick the widest one, like from here to here, and like the tallest one from here to maybe there. And you start making little chunks, right? You just slice these things up and, draw lines, so to speak, across them. And then, because you're starting with the widest and the tallest, you can break this problem up into smaller pieces and smaller pieces and smaller pieces. And once again, it's a recursive algorithm using divide and conquer. So please do look at the book because we're going to be asking you some questions about how all that works. It turns out that the divide and conquer technique is the big O notation is n times log of n, which is pretty doggone good. Okay, if you recall from the example we had last time, anything less than 1 to 1, oh, you're good. Okay, so n times log of n is less than 1 to 1 slope, so that is fantastic. Okay, so that's a good one. Now they show a bit of code on how this is done. It's not really pseudocode, it's just kind of thinking, okay? So here we go. So the point of S farthest from the dividing line. So I just did a dividing line and said, fine, here's my dividing line. Now which one is farthest from that? And then the set of points to the right of the line, that's between that. And then a set of points to the right of the line between these other two things, and then you just do it again, and again, and again, over and over and over, by just dividing this thing up into chunks, and then passing it where the distances are above or to the right of the line, so to speak. Okay. The next thing we're going to talk about is on page 53. They talk about permutations. So a permutation would be like... okay, here's a spy novel. You walk up to a keypad, okay, and you put some fancy spray on it and something, and you can tell that it's a 4-digit number, and it looks like 4, 6, 2, and 1 are the numbers that make up the code to be able to break into this cipher lock. But you don't know what order they're in, okay? So a permutation is how many different combinations of 4, 6, 2, and 1 are there, right? That's what it's about, right? It's how many chances are there of me getting this right. So if I had 4 items, then it turns out this is going to be one of those factorial things. It's going to be 4 times 3 times 2 times 1. So it'd be 24 combinations to try. So if the bad guys are coming, I got 24 of these things to try out in all the different, orders to make this thing work. Okay, factorial. Whew. Now there's a technique that they're going to show you on how this thing works, about how you would go about doing that. And this is kind of a weird one. And it talks about if n is an odd number, then swap them out, and if it's an even number, you swap that out. In other words, it just rolls through and just makes swaps those things out over and over and over again. Okay, so that's a cool technique. Now, hang on a second. You know, we've been talking about efficiency, right? About how we want things to be below the one-to-one slope on that graph that we showed last time. Sometimes we don't want things to be efficient. For example, let's say I had a cipher lock, and would it be best for me to have 4 digits on the cipher lock or 6 digits on the cipher lock? From a security point of view, 6 digits would be 24 times 5 would be 120 times 6 would be 800 something. See how it goes whoop, up really, really quick? Well, if there was like 800 something combinations, well then I'm going to be there for a really long time and get really bored punching in 6 digits over and over and over and over and over. So when it comes to passwords and those kinds of things, I do not want computational efficiency. In fact, I want on the opposite side, instead of having my work being below the one-to-one slope, when doing security like password complexity, I want it way on the other side. I want that factorial kind of a thing. Okay. The last thing we need to talk about is recursion and the stack. So what happens when you call this guy heap permute over and over and over again? What happens is there's a portion of the computer memory called the stack, and there's a portion of memory called the heap. And so this one is one of the ones that's kind of using the heap, but just bear with me for a minute. And so it kind of works like this. When a method gets called, what happens is like the machine says, I'm just going to take all the memory, all the variables that we got, and I'm just going to just tuck them away. So if you call that thing a second time, it's going to take, like, let's just assume there's 4 variables in your method. It's going to stack 4 numbers. And then if you call it again, it's going to stack 4 more numbers, and then 4 more numbers. And when the method is gone, those 4 numbers come off, and these 4 numbers come off, right? So the stack grows in size and shrinks in size, and grows in size and shrinks in size. But when you do a recursion, there's no opportunity for it to shrink. It just grows 4 and 4 and 4 and 4 and 4 and just keeps on going because it doesn't ever get back. I mean, it just starts over and over and over. The only way off is when it finally says, like in this case, output the list. You know, it finally gets to the point where it says, I want off the merry-go-round, and then the stack will finally go, boom. Now, it is possible that you could run out of stack. Now, to tell you the truth, this is not really, really, really a serious concern on modern operating systems. But, you know, maybe if you're running like on a smartphone or a small IoT device or something where memory is extraordinarily precious, then yeah, you might have to consider this. So if you have an infinite loop, like you forgot this get off the merry-go-round section right here, you forgot to do this n is equal to 0, what'll happen is your system will run out of stack and your program will crash. So yes, an infinite loop will definitely consume all of the stack, and bam, your program will go down. So the depth of the stack is how many times the recursion has occurred times how much memory is being used by that particular method. And so that's how you could figure out the stack. Okay, we have reached the end of this chapter. This was kind of a short chapter. Hope you guys enjoyed it. And we'll pick this up again with the next chapter.